So just for the sake of recording, I will quickly again say that a machine, we know that a machine is a device or anything that uses power to do some work, right? It takes available energy provided to it, transforms that energy into a form that it's able to use to do a work, or simply transmits that energy from the point where it gets it, the point of generation to the point of application. So anything that does work, that makes man's work easier, that provides ease of work is called a machine. And we said that there are basic elements. You have your prime mover, where the power or the motion to be transmitted is generated. And then you have a transmission system that takes that power, transmits it or transforms it into the power to be applied at the point of application. And that transmission system is made up of mechanisms and transmission units. Okay. Those transmission units are a couple of them. There are gear systems. That's one form of power transmission system, gear systems, where you have a shaft bringing power, okay? Bringing power from a prime mover. And then on that shaft, you have gears, which are toothed wheels, wheels that have teeth, okay? Toothed wheels that transmit or transfer that power to other shafts, to another shaft that also has gears. Okay, so the gears would usually mesh. That's the gear system. Then you have belt and pulley systems, right? Where you have pulleys that are attached to both the prime mover and to your point of application, and you have a belt that connects those pulleys together such that the give me 1 minute, such that the give me a second. All right, thank you. Thank you for waiting. So you have the belt and pulley system. Then you have the chain and sprocket system. You could also have even lead screws. Okay. All of those are power transmission systems. And in those systems, you have a number of elements. A number of elements. You have shafts. Okay. Shafts are basic elements that are used in power transmission systems. You have gears. You have chains. You have belts. You have pulleys. You have sprockets. You have keys. Keys. You will have things like lock pins, spline shafts, and the rest. Okay. Now, each of these elements require very serious thought, very serious design, very serious calculations. And that's what we are going to do in machine design 1, 2, and 3. Okay, we'll focus on the design of these machine elements. We'll do shafts, we'll do bearings. Okay, I didn't even mention bearings. Bearings are also very, very, very critical to machine transmission. We will do bearings. In this 400 level, we'll do shafts and bearings. Okay. When you come to 500 level, we'll do gears. We will do what again? I think we'll do belts. We'll do belt and pulleys, belt drives and pulleys, design of belts and pulleys, and maybe fasteners. Okay. But for 400 level, for this class, we will start with shaft design. Okay. Then we'll go from shaft design, and then when we finish shaft design, we'll now do design of bearings. So this morning, we want to quickly start with the introductory aspect of shaft design. I have less than 2 hours. I know the class is usually 3 hours, but I have something I must attend to by 10. And so by a few minutes to 10, I would have to end the class. So pay very close attention. I will be moving at a very fast speed if I can, and so that we can cover up all that we need to cover. Just give me a minute. Let me share my screen. Share that one. Share. Great. Please do let me know when you can see my screen.
Yeah, we can see, sir.
Your screen.
Great.
We can see
Excellent.
your
Thank you. Thank you. Thank you. So shaft design, that's what we're looking at. We will start by looking at the layout. What we'll do, we'll look at design of machines and machine components. I've already talked about that generically. Then we'll define what shafts are. We'll look at shaft layouts, we'll look at materials used for shafts, and then we'll go into the design of shafts for stress. We'll look at the various approaches you could use in designing shafts. Okay, so I've talked about what machines are, how they help to transmit power to overcome loads. We've talked about that already. Okay, they transmit power or motion from one place to another. So power transmission systems are very, very, very key in the design of machines. And the components that make up the power transmission system, we've identified shafts, we've identified gears, bearings, keys, pulleys, belts, chains, sprockets, cams, etc. All right. The whole essence of these design calculations that we're doing is to ensure that we size or we specify the sizing of all these components such that they are able to function safely without failing structurally. All right, without failing structurally. That means that we do not want them to their structural integrity to fail. Okay, so we really pay a lot of attention to structural strength. Okay, and we look at it based on load stresses, the stress generated inside your structure as a result of the load applied to your structure, whether we're dealing with a gear system where you have a shaft and then you have gears on that shaft, as we will do in this class. Okay. Then there are several other reasons why a system could fail, but we are looking particularly at the structural failure of the machine or the component, as the case may be, because a machine can be said to have failed if one of the components fail. And once one component fails, the whole machine begins to malfunction, right? So what are shafts? We define shaft as a rotating member, okay, that is usually of a circular cross section. So if you take a plane and you cut the shaft transversely and look at the end, what you see should be a circle. All right, so it's a rotating member. Usually you could have some shafts that are not, they do not have a circular cross section. Some can be oval, some can be star shaped, some can be even squares, right? But it becomes really difficult to manage all the other things that need to be coupled to the shaft to make it transfer its power to a different shaft. So shafts usually have a circular cross section, and the function of the shaft is to transmit power or motion. So a shaft, again, is a rotating member. Note, underline the word rotating. Rotating. Okay? It's going round and round and round. It's a rotating member, usually having a cross-sectional area that is circular, and it's used to transmit power or motion from one point to the other. Okay? So the functions of a shaft, one is that it supports whatever elements you have. So it supports the gears, okay? It supports the bearings, And if you have pulleys, even pulley systems need shafts to support them. So it supports those elements, and it also provides the axis for rotation. Okay? It provides the axis for rotation. So when you have gears, you have pulleys, flywheels, cranks, all of those things that rotate. For them to rotate with me, it means that they have an axis about which they are rotating, right? And our shaft provides that axis. So one, it provides support for those elements, okay? Gears, pulleys, flywheels, cranks, and the rest. And it provides the axis for rotation. Now, it also allows for the tangential force and all of that to transmit the power that needs to be transmitted. So if you have a Okay, so we said that the power to be transmitted is transmitted through the shaft. So imagine that you have a motor, right? Motors usually have some features that allow you to impute a shaft and couple the shaft to the motor. So as the motor is turning, the armature of that motor is connected to the shaft. That shaft is the one that carries the power. Okay, so as the shaft rotates, it has that the power that is causing it to rotate is there. Now, when you are able to connect that shaft to another shaft, is able to transmit, is able to transfer that power from the motor to the shaft that you want the power to be transferred to. And it usually does that using tangential forces. Okay, those are shafts. Now, there are two other things that people confuse as shafts. One is an axle. Okay, an axle is a non-rotating member. Okay, that carries no torque but is able to support, is able to carry the weight of other rotating members like maybe wheels and pulleys. Okay, so the difference between an axle and a shaft we said is a rotating member. So if you have a long piece of metal circular in cross-sectional area that rotates, okay, then we call it a shaft. And you can fix your power transmission elements to that shaft, gears, pulleys, and all of that. You fix them tightly so that as the shaft rotates, they also rotate. That's a shaft. But if you have a long piece of metal that is circular in cross section, but is not rotating. Maybe it's fixed firmly to a frame. Okay, but that member carries other rotating members. Maybe it carries a wheel that has a bearing between the wheel and our member, our piece of metal, right? And it allows the wheel to rotate freely, but it carries the weight of the wheel. That is called an axle. Okay, that is called an axle. When you look at a car, you always hear axle, axle, axle inside the car, right? Aha. The axle of a car is not actually an axle. It is a shaft. That word axle came from when we started having chariots. When you had chariots and you had the structure where people would sit. Now, under that, there was an axle. There was a long member, either of metal or wood, that was fixed. And then on that, they now attached wheels that were allowed to rotate freely. So as the horse is pulling the chariot or the cart, the wheels are free to rotate by themselves on that member. That member was called an axle. And that followed it into vehicles. When they made vehicles, they called these things axles, but they are actually shafts. Shafts rotate. Axles do not. Is that okay? Axles do not. So they do not transfer torque. The axles themselves, they do not transfer torque. So let's know that. For a shaft, the shaft carries torque and transfers that torque to the gears or pulleys, and then those ones in turn transfer the torque to another gear or to another pulley, and the process of transmission continues. A spindle is actually a shaft, but it's a very, very, very short shaft that usually imparts motion to either a cutting tool or a workpiece. Okay, so if you have a rotating member that is very short and its function is just to transfer motion to a cutting tool or to a workpiece, then that's a spindle. So when you go to the lathe machine, you hear spindle, spindle, spindle. We're talking about a very short shaft rotating that transfers, its function is to transfer motion or to impart motion. So you would usually have a chock or something that you clamp your workpiece to, right? And then this, as the spindle rotates, it turns the workpiece also. So we've defined three things. We've defined a shaft, we've defined an axle, and we've defined what a spindle is. Any question at this point before we move on? Any question? No question. Great. So let's move on. Let's talk about shaft layout. Okay. How do we geometrically arrange shafts and shaft elements such that they transmit power? It's very, very, very important. In your design, there are certain principles that you need to follow, okay, in transmitting power. Okay, so a shaft usually accommodates shaft elements, and those are bearings, gears, pulleys, or it could be sprockets, etc. Okay, so early on in your design stage, in the ideation stage, you should specify, your general shaft layout. If this is my shaft, where will my gear sit? Where will my bearing sit? What should be the distance between my gear and my bearing? What should be the distance between my pulley and my bearing? And all of that. That's what we call layout, shaft layout. All right. And when we need that shaft layout when we come to our calculations, because we will need to do bending moment diagrams. Okay, we will need to do force diagrams. All right, and those values, we pick the maximum of those values and put in equations to calculate. So your free body diagram is needed. You must know your shaft layout. Where exactly are you fixing your gears or pulleys? Where exactly are you fixing your bearings, as the case may be? All right. Now, we generally use a stepped cylinder. Okay, and well, you will see stepped cylinders in the next a few images. So what we mean by a stepped cylinder is a cylinder that does not have the same cross-sectional area or diameter along its length. So we might start with a portion that the diameter is, let's say, 10 millimeters, right? Oh, well, it's very difficult to find standard shaft sizes at 10. Let's say 25 millimeters. And you have 25 millimeters that runs for, let's say, 30 centimeters. And then the diameter changes. From 25, it jumps to 30. Okay, it jumps to 30. And so you have the next section of that shaft running, has a bigger diameter of 30 millimeters, running for maybe another 50 centimeters. And then it may step down back to 25. We call those shafts stepped. Stepped, because the diameter changes. When we draw the cross section, it looks like rectangles that get bigger and smaller as the case may be. And the advantage or the use of having stepped, I think I should give me a minute. So that I can do a sketch and you see what I'm doing. What's that my app called? Concepts. Wait. New drawing. Okay, so let me come back to Zoom and share my screen. Share concept. Please let me know when you can see my screen. Can you see my screen now?
We can see it, sir.
Great. So when we're talking about stepped cylinders, usually I'm sketching with my mouse, so it's not going to be very perfect. So if I've got a shaft like that, right? And I now have a bigger, okay, all right. And let's assume that we now have a bigger one again. Okay. And let's assume that that one now steps back down. Okay. We call this what? Stepped. This is a stepped shaft. All right. If we're looking at the cross section, it will probably look something like this. So you would see, okay, you may not, it may just be, if it's made of the same material, right? Pardon my drawing. Okay. And this comes back down. This comes back down this way. I need to turn off my notifications. Okay, can we all see that? Give me a minute. Oops. Okay, let me just skip it off. So this is what we call stepped shafts. And the advantage, the advantage or the advantage of having step shaft is that one, you have these shoulders. We call these guys here shoulders. These are the shoulders of the shaft. Okay. These shoulders, they provide a means of axially locating. So in this shaft, please follow me very carefully. If we start from this point and we journey, where's my color? If we start from this point and we journey along the length of the shaft, we call that direction an axial direction. So anytime you hear us saying axially, we are saying along the length of the shaft. If we turn to the cross section and we start at this point now, and instead of going along the shaft, we start at the center axis of the shaft and move in that direction. We say we are moving radially. So anything that starts there and moves that way, okay? It starts from the center and moves out. It starts from the center and moves out. Those directions are called radial directions, radial. But if it's along the length of the shaft, it's called what? Axial, axis, along the axis of the shaft. So shaft shoulders help us to axially locate shaft elements. For example, I wanted to fix a gear system here, right? I wanted to fix a gear system here, right? So don't mind I should not have done it that way. Let me just use a circle. Okay. What my shaft shoulder will do for me is to provide a stop. So when I fix this shaft in, because the inner diameter of my gear, I say shaft, my gear, when I fit my gear into the shaft, if I want this gear to sit on this shaft, then the inner diameter of my gear should be very, very, very slightly bigger than the diameter of this shaft. Or if I want to use interference fits, we will look at a little bit later. Then the shaft inner diameter, the bearing or the gear inner diameter, needs to be the same size as the shaft diameter. Since this one is smaller, this guy will fit in as we are moving axially. The gear will fit into the shaft and it will move until it gets to that point where the shaft's the gear's inner diameter is lesser than this shaft's diameter. So it stops. So shoulders provide a very, very good way of locating your shaft elements axially. Okay, so you feed them and they run until they stop and you can lock them there, either using if it's an interference feed, you keep pushing it until it stays there and it stays permanent. If you're using a key, you fit it to that point and your key is there to lock it in place. All right, so shaft shoulders provide a means of axially locating your shaft elements. Okay, going to go back to my slide. And then the other function that they do is they allow to carry thrusts. Okay, thrusts are loads that are transmitted along the length of your shaft. So thrust loads are axial loads, particularly when you have helical gears. You have gears that the tangential or the force being transmitted is not perpendicular to the axis of rotation. All right, they are inclined at an angle. Those gears have forces that act both radially and axially. Okay, so when you have shaft shoulders, they act one of their functions is to provide support for thrust loads. Okay, so there is something that your load is resist, or there's something that resists your axial loads. Okay, now remember that if we connect our shaft to a motor, your shaft is turning. Okay, it's turning, is rotating. The shaft is a rotating member, it's not an axle. Now, as the shaft is rotating, if we put a gear onto that shaft, there must be something that transfers the rotation or the power in the shaft to your shaft element. Okay? So there are elements that we call torque transfer elements. They transfer the torque from the shaft to your shaft elements, either your rotating elements, your gears, your pulleys, your bearings, and etc. Okay, one of those elements are keys. Keys. When you hear keys are not they are not the normal keys you use in opening and locking a door. All right, they are either, well, I'll show you examples. So you have keys. We do design of keys in this level. No, we don't. You have keys, you have splines, you have set screws, you have pins, you have press or shrink fits, and you have tapered fits. All of these are used to transfer torque from the shaft to your gear or to your pulley, as the case may be. So let's quickly look at a few of them. So the first image I have here gives us an example of a key. All right, so you see the shaft. The shaft is there, and then the key, there is a groove usually in the shaft, and then there is a keyway, an opening in whatever it is you are fitting your shaft to, right? So you now have a key that sits inside the shaft and also protrudes into your element, either your gear or your pulley. Okay, so that when the shaft turns, okay, your element that has been fixed to your shaft also turns along with it. The key will move with it. Do you understand what I'm saying? That's the key there. So keys are one way of transmitting torque from your shaft to your gear or your pulley. Now, you also have splines. Splines are like, they are teeth, very, very large teeth on shafts and inside hubs that allow for, as one rotates, the other also rotates, they allow for the transfer of torque. So you can imagine that this is a spline, this is a spline shaft, that's a hub with splines. When you fix this shaft into your hub, you see that the hub has 1, 2, 3, 4, 5, 6 of those grooves that have been cut out to the shape of the splines on your shaft. So they fit in exactly. They are like gear teeth. They lock in. So as you turn the shaft, whatever had those blind hubs on the inside will turn with the shaft. All right. This is a cross section that shows you. This is a transverse view. Okay. Spline shafts are used in many purposes, particularly when you have very, very, very high torques. If you have very high torque to transmit between shaft elements from a shaft to a gear, use of keys might not be sufficient because keys have limited sizes and there's a limit to the torque that they can transmit. When you have very large torques, the best torque transfer element to use are splines. Okay, it will transfer your torque very easily from the shaft to whatever it is that you're transmitting that to. Great. Next is set screws. Set screws, and these are usually for applications that do not require very high torques. All right. So we use this a lot in our mechatronics projects. We are dealing with little components. Your servo motors, they use set screws. So at this end there, you fit your shaft into this, and then this set screw is screwed into. So it goes until it holds the shaft in place. So as the shaft turns, this will also turn, or as your gear turns, the shaft also turns. Okay, set screws are one way of transmitting. Then you have I've not put. Okay, you have pins, not press fit. You have pins, right? Pins run through your element, either your gear or your what is it now? Or your pulleys, whatever it is. It runs right through the shaft. So if you look at this cross section, so if this is what you want to transmit your torque to from your shaft, then you have a hole through that element and you have a hole through the shaft, and your pin goes through it. You can have a perfectly cylindrical pin. You can have a tapered pin. All right. So as the shaft rotates, okay, it also carries along the element that is fixed to it. Those are pins. So these are set screws, these are pins. And then you have interference fits. Interference fits is a case where you force your shaft is either a little bit bigger or exactly the same size as your hole. And so when you force it in, friction, okay, the friction between the shaft and the hole it enters causes them to stay. So as one rotates, the other follows it. All right. But if you have very high torques, you can't use interference fits. If you are using interference fits, then you will need your shaft to be a little bit bigger so that the friction between them is more. Now, somebody will ask, if the shaft is bigger than the hole, how will it enter inside? That's where you have your what you call shrink fits and all of that. The shaft is shrunk, okay, and then it allows to enter. It's usually when something is cooler, it shrinks. When you heat it up, it expands. Okay, so there are a lot of methods that they use to shrink the shaft and then fit it in. And then when it comes to its normal temperature, it will expand, right? As it expands, it fits into that hole very rigidly and is able to transmit torque. So these are torque transmitting elements. We've called them keys, splines, set screws, pins, press or shrink fits. tapered feet, etc. All right, let's move on. Shaft layout. We started talking about the shaft layout. Now, what should be your guide? There are a few things. One, bearings. Where should you locate your bearings? Your bearings, the function of your bearings is to support the shaft, okay, and allow it to rotate freely. Remember, your shaft is a rotating member, okay? So if you want to support your shaft and you hold it, by holding it, you might prevent it from rotating, okay? So bearings have been designed to hold the shaft, to support the shaft, okay, so that it is supported rigidly as it's rotating, is not moving here and there, to support the shaft, but also to now allow it to rotate freely. Now, where you locate your bearing is very, very critical, okay? You locate them so that you are providing adequate support for the shaft, okay? And you want to also locate them such that you minimize bending moments. Bending moments will cause a shaft to bend, all right? If I will annotate on my screen very quickly, you will see. If I have a shaft that is straight, right? And I fix a bearing there, and I fix a bearing here, right? And on this shaft, I have a gear that is placed here. Okay. Now note that I have provided, because these bearings are here, they provide support at that point. They provide support at that point, right? So, but this gear that I've placed here has a weight that acts downwards, right? So the tendency of this shaft is to bend like that. Okay. So bending moments cause a shaft to bend. Now, if the shaft bends or if it deflects in the middle that way, because these are where my bearings are, the rotation of this shaft will be problematic. It will have a lot of vibrations. Because okay, it's in this 400 level. I think it's EMA 30, no, EMA 405. You do balancing of rotating members. Okay, when you have a shaft that does not have its masses evenly distributed about the axis of rotation, you have vibrations, very serious vibrations. Okay, those of us that drive cars, when you drive your car to a certain speed and it starts vibrating, you know that you need to go and do wheel balancing. It means that all the masses of your wheel are not evenly distributed about the axis of rotation. And so you have vibrations. So we want to minimize deflections and bending of your shaft as much as possible. And so when we are locating our bearings, right, we want them to be located in such a way that bending moments are minimized. Okay? And so for most bearings, for most shafts, we recommend to use two bearings, usually at the extreme ends of the shaft, to allow for your gears and pulleys and all of that to be located within, usually. Okay? But if your shaft is excessively long, the longer your shaft, the more likely it is to bend, even under its own weight. So when you have excessively long shafts, then you can use 3 or more bearings to support the shafts. You have a very long shaft, you can put one bearing in the middle, one at the end, and the other at the opposite end, and that will provide adequate support to prevent bending moments. The problem with having more than 2 bearings is the problem of alignment. Your bearings need to be adequately aligned. They have to be perfectly aligned so that the rotation of your shaft does not have vibrations. If you do not align your bearings properly, you have a lot of uncomfortable vibrations that will facilitate failure. They will enhance failure quickly. Okay? So use 2 bearings as much as possible. When you have very long shafts, then you can use 3 or more, but you must ensure that you align them properly. And it's always very, very difficult to align shafts. Okay. So that's bearings. And I will show you a little bit. When you have things that require constant maintenance, right, is good to leave, for example, like maybe a fan or something, or even a pulley system where you have, for example, in your grinding machine, the pulley that is on your motor, your prime mover, and the pulley that is on the unit that is causing the grinding, the threaded shaft, right? The pulleys are outside. The bearings are within, or maybe let me not talk too much because as I'm describing, you might not see it. I'll show you images in a short moment on bearing location. Now let's talk about component mounting. Okay, where you mount your component is based on function. Where exactly do you want your gears to be? For something like a gearbox, where depending on the size of the gear, depending on the space available to you, all right, you will locate your gears along the length of the shaft, depending on where you want of course, within the limits of the available space, right? And all of that. So it's basically based on function. So where you locate your gear, where you locate your pulley is based on function. For a gear system, we do not need, because particularly that we must lubricate gears. Okay? Because we must lubricate gears. Gears are placed between the bearings. So you will have your casing. You have your casing, and then your bearings are usually inside that casing or housing. You locate your bearings there, and then between the bearings, you now have your gears. Is that okay? Between them. For something like pulleys need to be located externally for ease of access. Okay? Your fitting of the belt. If you locate your pulleys within your bearings, it's going to be very, very difficult to do changing of your belt if your belt becomes slack and you want to adjust it, tighten it if your belt develops a problem, and you do all of that. So usually you don't. For those of us that have a Toyota Camry, our timing belt can cut. Once the timing belt cuts, the mechanic has to come, he has to lose this, lose that too. And even at that, your is just a cover that has been placed over the timing belt to prevent dust and all of that from affecting it, right? But you have to remove all of that. You have to remove the belt and replace it, etc. Okay, so mounting is dependent on function. Gears are usually located in between the bearings. So your bearings are located at the two extreme ends of your shaft, and then your gears are located within. All right. For things like pulleys and sprockets, the pulleys are located external, outside the bearings. Okay. Then your shoulder location, your shoulders should be located where you need your gears and your pulleys to be. Okay, so that when you mount them, they can come all along your shaft and stop at your shoulders, exactly where you want them to transmit their power. So these are two cases of a shaft layout. The first thing you do is to do a schematic, drawing of where your shaft will be. So the first example here is a case of a bearing, right? The second example is a case of a pulley and a fan. Okay, so let's start with the first case. I have two helical gears. Okay, they're helical gears because of the direction of their teeth. You have two helical gears to be located. This stuff that you see here is our bearing. It's showing us where our support will be. So we first locate our bearings, and then we now locate our shafts inside the bearing. I say inside. Well, if I say inside, that's the wrong English. Not inside, between the bearings, right? And so this is located there. You would usually what's my annotation? You would usually identify or specify the distance between this from the bearing to, when we start doing calculation, you see that all you must know, because when you are doing bending moment calculations, all of that, you'll be required to know the distance, because the bending moment of the force acting at this point from this given point depends on the force and the distance between this. So we must know that distance, right? So we would usually know the distance between these components. Okay. So you will first just identify where your bearings, where your, oh, why did my video go off? Oh, it's a different video. Why did you select? Great. All right. So when you locate these, then you can now, in the B part, you can now begin to say, okay, how should my shaft be? All right. So when you see, look here, I have stepped shafts. The first step, all right, stops at the shoulder where the bearing is supposed to be located. So when I'm imputing my or installing my bearing, I fit it on that shaft and push it axially until it stops at the shoulder. All right. Then I now have a slightly bigger diameter there, all right, that provides the shoulder for the bearing to stop, but it allows the gear to enter and go until I stop at that point. Okay. For the second gear, I fit it from the other end. Now, but there's something here. There's something here. There's what you call what's the name now? Do I have it somewhere here? A sleeve. No, is it a sleeve? A locating collar. This, let me change my color. No. Blue. This stuff here is a locating collar, okay? That one there. So what it does is, now this is the main shaft. The main shaft is a little bit is quite small. So when we fit this in, when we fit the gear in and it has a key, we now use the collar to also provide support at the other end so that the gear is not free to move along the length of your shaft. It can't move axially. It can just stay there. Okay. So we'll have that step. So first procedure is to identify where your shafts, first your bearings. Bearing will be here, bearing will be there. And that's really, really governed by the housing for a gear, for example, the housing of the gear. Your bearings are located in the housing. So what is my space? We locate my bearings. Then I put my shaft in, my gears in between those two bearings. Then I can now begin to step. Oh, okay. What then should be my shafts? Okay. So I have, let's say, 25 millimeters running for for what length? Then we increase it to 30 millimeters for one length and all of that. Okay. Now the second instance is the instance of the having a pulley that is run by a belt. So you will note that this pulley is not in between my bearing. Okay, it's external to that arrangement. So look at my bearing. My one bearing is there, the second bearing is here. What is in between this guy is the fan. So there is a fan that is turning to provide maybe some form of convection, air, create a draft in a system, right? So to turn the fan, power has to come from the prime mover, maybe the engine, right? And so we have a pulley system that from this you see that it's a V belt that will sit there. But this pulley is external. Miracle, Agbo, stop touching your screen. I'm the only one person permitted to annotate. Okay, so our shaft, our pulley is external to the bearing. So we fit this bearing. Before you fit this bearing, you must have put in your fan, then you fit this bearing, and then you can fit your pulley. Okay, and there is examples of you can see that those are set screws. A set screw is used to attach the fan to its shaft. Okay, these are also what do you call these ones? These are sleeve bearings that also use set screws to be located on. All right. So shaft layout, before we start doing calculation, your shaft layout must be there. And that should be determined in your ideation stage, okay, before you come to design calculations analysis. For all the problems, for most of the problems, if not all the problems you'll be dealing with in this class, your shaft layout is already given. So what you are tasked with is to size the component of the shaft, to select the correct gear and all of that, correct bearings, and then you calculate how many teeth should if this is the power you are transmitting, what should be the diameter of your shaft, how many teeth should it have, and all of that. All those calculations will be 500 level for gears itself. This time we're going to focus on shafts and bearings. All right. Any questions so far before I run from here? Any question? While you're asking your question, let me take a sip of water. Any question? Who is calling me? All right, silence means no question. Let me look at the chat. Oh, okay. Someone is saying that if my video is off, it's better for them. Okay.
Excuse me, sir.
Yes.
Okay, I just want to get clarification on this. The sleeve, the screw, is it sleeve screws? Now, on this second shaft layout that we have here, do we have them on the shaft itself and on the fan that is installed on the shaft, or we just have them on the fan alone but not on the shaft? Because please, can you just come on that part again?
Sorry, I muted myself. It depends on the what do you call it now? The torque transfer element you decide to use. Okay, it depends on for your fan. In this case, both your fan and your pulley are using set screws. Set screws to attach these elements to the shaft. Is that okay? The collar, I don't know exactly how the collar, the sleeve bearing works, but that looked like something that would attach. Of course, the inner part, if and there are two ways when we come to bearings, you can either fit or fix the outer ring. So that one is fixed and the inner ring is allowed to rotate, or you fix the inner ring and the outer ring is allowed to rotate. Those are two configurations for your shaft. Usually, you can fit the inner ring is fixed firmly to your shaft. The outer ring is fixed firmly to the body, and then the balls or the rollers in between allow those two to rotate freely. Details on how that is attached, I cannot say now. When we come to bearings, we will look at it. Even though we do not actually deal with this kind of bearings, what we'll be looking at is angular bearings, deep groove bearings, and the rest. Did I answer your question?
Yes, sir.
Not convincingly. When we progress, you will gain understanding. All right. So let's talk about materials that are used for shafts. Can we use any material for shafts? Plastics, wood, and the rest? Yes, you can. But there are conditions. Since we are going to be transmitting power and we're going to be transmitting torque, we want to design our shafts in such a way that they do not fail structurally. Okay? So the first condition is whatever material you're using for your shaft, they should have high strength. High strength. Meaning they should be able to carry and withstand high torques, high loads, without bending, without failing, without what's the word I'm looking for? Without failing. Is that okay? They should have high strength. 2, they should have good machinability. We should be able to machine them because we're talking about shafts having shoulders and all of that. We should be able to cut out the shaft to the size we want. If your material cannot easily be worked on, we cannot easily remove portions of it, then we'll have a problem. It might have very high strength, but we can't shape it into the particular shape that we want. That will be a problem. So it should have high strength, but it should be able to, it should allow us manipulate its form. Okay? 3, it should have very low notch sensitivity factor. And the notch sensitivity factor talks about the amount of stresses and the failure that is possible from a case where you have a shaft that suddenly reduces its cross-sectional area. Let me show you what a notch looks like. A notch will be something like this. So if this is my shaft, that's the usual cross-section of this shaft, right? A notch is a sudden change in diameter. So if I'm looking at it cross-sectionally, it will be like a dip that way. That's a notch. And with notches, there's a lot of stress concentration around the notch. Okay? So when we talk about a notch sensitivity, we are saying that material should not be very sensitive to notches. So if there is a notch and it accumulates stress and easily causes the material to fracture, the word I was looking for at that point was fracture, to fail, then the sensitivity is high. All right. You can go and read up on what notch sensitivity is. So what we want is a material that has very low notch sensitivity factor. It's not very sensitive to notches. Is that okay? It can manage notches properly. And then we also would have loved to have the material to have good heat treatment properties. Heat treatment increases strength. So this goes with high strength. If you heat your material, it increases strength, but also helps the material withstand very high temperatures. So because whenever your shaft is rotating, it will generate a lot of heat as a result of its motion, and particularly with the materials used. So heat treatment is needed to strengthen your shaft and to also provide it with some properties that make it to be heat, to carry a lot of heat and to resist wear. Okay. The next property is that of wear resistance. Your material should have high wear resistant properties, high corrosion resistance properties, because you will need lubrication. Okay, you will need lubrication to allow for 1, heat management, 2, to allow for to reduce wear as the machine elements or gears are touching each other constantly engaging and disengaging. Wear should be minimal. Okay, so your material should have very high wear resistance. Is that okay? And so because of these properties, many shafts are made from steel. Because of the high strength of steel, it has very good machinability. We can form it into whatever shape we want. It has a very low non-sensitivity factor. You can treat steel, and it has a high wear resistance as well. Okay, so steel, and to have the strength that we are needing, you need low carbon steel. Low carbon steel. That's either cold drawn or hot rolled. Cold drawn steels are usually stronger than hot rolled, but they are very difficult to achieve. So you can use either cold drawn or hot rolled steel. They have the advantages, they have their disadvantages. And an example is ANSI 1020 to ANSI 1050 steels. Now, this ANSI stands for American National Standards Institute. Okay. Sometimes you will see in some places they will call it IC, AISI instead of ANSI. ANSI, ANSI is the American National Standards Institute. But when you come to AISI, is the American Iron and Steel Institute. Okay. They're the ones that specify, oh, if you have a steel with this percentage of carbon inside, this is the code for it. All right. And then some have a little bit of other rare metals added inside, either tungsten, manganese, magnesium, and the rest. No, not magnesium, manganese, I think. Okay, so ANSI 1020 to ANSI 1050 are very good materials that we use in creating or we use for shafts. Okay, either cold drawn or hot rolled, different steel grades. Okay, and the steel grade depends on the percentage of the carbon that is inside. If you have applications where you want you want extra strength, then you have to heat treat. You have to heat treat your metal. So I think I've talked about this, that shafts generally are hot rolled, okay, and then they can be called cold drawn. Cold drawn shafts are way stronger than the hot rolled shafts, but they usually have very high residual stresses. The concept of residual stress is when you are forming the shaft, right? Stress is generated inside that shaft member. Stress is force per unit area, okay? It's distributed along the length of the shaft. Now, when you finish working on that shaft, if you are cold drawing means you hold both ends of a piece of steel and you pull it apart, you draw it with a large force, and then in drawing it, it is stretched out. Okay, that's what is called cold drawing. Is stretched, and of course, as it's stretching, the diameter becomes lesser and lesser and lesser. When you finish, you can carry out turning operations to make sure that this thing is perfectly circular, the cross-sectional area, and then you can grind the surface to smoothen it, and all those other processes that you were engaging, right? But cold drawn steel, when you cold draw it, because of the forces used, stresses are developed inside the shaft that they are not relieved when you stop drawing them. So they still remain inside the shaft. And when you come to use the shaft, additional stresses will enhance easy failure. Okay, so we want to reduce residual stresses a lot. Fault lines, fractures usually begin at places where you have residual stresses. So the shaft is working normally, and then it just fractures, it breaks. Wow! What happened? Oh, our calculation is because of residual stresses. So there were already stresses inside from the manufacturing of the shaft. And then you now, in the use of the shaft, new stresses were developed. And at that point where you have residual stresses, was those stress add. For the other points where there were no residual stresses, it can cope. But now the stresses are beyond what the material can take. And then it fractures, it fails. All right. So what we usually do is we heat the metal up until it's close to its melting temperature, and then we begin to draw or we roll. We have very large, what's it called? Wheels that the metal is drawn through, and as they are rolling, they will press it to the correct dimension. for hot rolled metals, as the metal is cooling down gradually, what happens is your stresses are relieved also. So hot rolled metals have lesser residual stresses than. I should not be teaching you all these things. Professor Bam should have taught you guys all of this. So just remember all the lectures that Professor Bam taught you about this. So our own is just to take the material and apply it. Okay. So you see the effect of residual stresses. They may cause distortion to the shaft when it's being machined. Okay. They can cause problems when you are cutting in slots for your keyways. Okay. They can cause all of those problems. Okay. Significant strengthening can be achieved from heat treatment, and then we have some materials that are already heat treated. ANSI 1340 50, ANSI 3140 to 50, ANSI 4140, ANSI 4340. All of those are heat treated, or they can be heat treated. All right, when you need shafts that need that extra strength. Okay, but of course, with extra treatment to your shaft, the more expensive it will be. And you want your design to be as cheap as possible. So if the what's it called? If that level of strength is not required, you don't need that level of strength, then avoid it and reduce your cost. Okay, it's not that you just be selecting, I want the best. No, it's not just the best that's available. Your design, does it require that much strength? If it does, fine, then you go for it. The cost is justified. But if it doesn't, you are just causing the overall cost of your design to be higher for no reason. Okay. Again, shafts do not need to be surface hardened. You don't need to do surface hardening for shaft, except if you are going to use those shafts or part of those shafts as a surface for journal bearing. Okay, because for journal bearing, the shaft is in direct contact with the bearing and is rotating in, so you would need to harden the surface of it. Is that okay? And the material choices for surface hardening, you have carburized grades of ANSI 1020, ANSI 4320, ANSI 4820, and ANSI 8620. Is that okay? All right, so the properties of your shaft, okay, the properties of your shaft at the end of the day, they locally depend at given points on your shaft length. Depends on its history. How was it made? Did you code work it? Did you code form it? Was it rolled first? Did you include fillet features? Was it heat treated? What kind of quenching did you do? And what medium did you use? Okay, all the things that were done to it affect the property. So when you see the blacksmith doing various things, right? He heats his metal to a given temperature, he brings it out, he hammers it into shape, then he dips it into a quenching media, either water or sand or oil. All of those things impart certain properties to the shaft or to the metal in question. And so you need to understand, if you do not have the data sheet for a particular material, shaft material that you're buying, then you ask, so how did you, was this shaft cold drawn or was it hot rolled? Okay, did you quench it? If you hot roll, what was the quenching media, for how long, and all of those things? Then you are able to have an understanding of what its properties could be like. Great. So standard shaft sizes. We are finished with materials. When you are doing a design, right? Because designs can vary from one person to the other. Okay, you may now have this one person may say, no, me, I want my shaft to be 7 millimeters in diameter. Why? For this reason, for that reason, for that reason. Then another person say, no, I want my own to be 8.5. Another person say, I want my own to be 9. So with each person that you have designing something, if they have varying values for their shaft diameters, then you have to have a system that does bespoke bespoke manufacturing of shafts. And bespoke products are usually more expensive. The economics of mass production is that the more of the items you produce, the lesser the unit cost of producing the material. Okay, so if because of varying sizes, people's design requirements, you now have varying this thing, then it becomes a problem. Before you do your design, you have finished your design, then you now send the manufacturer, please go and make me a shaft that is like this, like this, like this, like this. And then the manufacturer will go and take time to make the shaft before it comes back. But all of that is solved by having standard shaft sizes, that when you go to the market, these are the sizes of shaft that you can get. And so if your shaft, the one you want, is particularly lesser than the standard shaft, then you buy one and you bring it to your workshop, put it in your lathe machine and turn it to reduce the shaft size until it gets to the size that you want. Okay, so manufacturers produce shafts in standard size. When you go to market, you just pick a certain standard size. And other machine elements have also been designed in line with standard sizes. So if you go to the market to buy a bearing, the bearing, they will ask you what size. They're asking for the size of the internal diameter of the shaft, of the bearing, because it's designed to fit a particular shaft. So what are the sizes or standard sizes of transmission shaft? Transmission shaft, please note. You can have other shafts that are not transmitting very high power and high torque. Those ones can be any size you want. But for transmission shafts, the minimum size you would find, standard size, is 25 millimeters. When we say 25 millimeters, we mean the diameter of the cross-sectional area, right? So from 25 millimeters to 60 millimeters, we have standard shaft sizes increasing in 5 millimeter steps. So if you go to the market, what you find is 25 millimeter diameter, 30 millimeter diameter, 35 millimeter diameter. Are you following the increment? 40 millimeter diameter, 45, 50, 55, and 60. From 60, it starts increasing in 10 millimeters. 60 to 110 is 10 millimeters. So 60, then 70, you will not find 65. 70 millimeters, then 80 millimeters, like that, until you get to 110. When you get to 110, it starts increasing in 15 millimeter steps until you get to 140. Then from 140 upwards to 500, it increases in 20 millimeter steps. Okay? These are the cross-sectional areas, right? The diameter of the cross-sectional areas. When you talk about the length, standard shaft sizes, how they manufacture them, they come in 5 millimeters, 6 millimeter, 7 millimeter lengths. That's how you get them. We're drilling a borehole, and the machine they brought, they had those sizes, 5 millimeters. That's how it comes. All right. And so you're able to know, if I want to go in this depth, you know how many of those shafts I will sink in and all of that. So don't forget this. When we come to calculation, depending on the load, depending on the material type, depending on how we have arranged the layout of our shaft, okay, we will determine the correct size. And when we come to the design of shaft, I will explain that. When you have calculated and you have an answer, then you come to your standard shaft sizes and select a shaft in line with what you've calculated. Now, what you have calculated gives you the minimum size that is required to transmit the amount of force that you are saying you want to transmit. The minimum size. So if, for example, I've done my calculation and my calculation gave me 34.5. Please follow me carefully. It gave me 34.5 millimeters, right? And I come to the market, I will not find a shaft that is 34.5 millimeters. I will find a shaft that is 30 millimeters in diameter, and I'll find a shaft that is 35 millimeters in diameter. What 34.5 tells me is that that is the minimum diameter I should have if I want my shaft to transmit this force without failure. And so common logic will tell you that you cannot select a size lesser than what you've calculated. If you do, then you're already planning for failure because your calculation is telling you that if these are the forces you want to transmit, if this is how you have arranged your shaft and your shaft elements, and if this is the material you say you want to use, then the diameter of your shaft must at least be this so that it does not fracture, it does not fail, it does not have excessive bending. Because these are what we mean by a shaft failing. Either is deflected excessively or it has fractured. Is that okay? And the likes. Okay, so with 34.5, you are asked to choose the next available shaft, standard shaft size above your calculation. So I will choose 35. Now, what if my calculation gave me 30.235? 30.235. Somebody might say, let's round it down. No. 30.235 is bigger than... Please mute your mic. Whoever is that unmuted, please, can you mute yourself? So 30.235 is bigger than 30. So you must, by practice, by standard, you should select the size, that's the higher size to that. So 30.235 falls between the standard size 30 and the standard size 35. We will still select 35. Okay? If you want, you can go and select 40, no problem. But the bigger the size you select, the stronger your shaft, but the more costly your shaft will be, because more material means more cost. And then the more space you will require to take that kind of shaft. So that's why we select the next one higher to that. Okay, to ensure strength, right? And to also minimize how much we will spend in terms of material cost. Did everybody understand the explanation I gave? All right, let's move. Design of shafts. I have about 20 minutes. I will just introduce this and then we will go. Design of shafts. Now, you can design your shaft on the basis of strength. On the basis of strength. That means strength is, remember when we're doing, what was it we call this? Specifications, design specifications, and the criteria for assessing, all right, your design. We mentioned a number of things. Strength was one of them. Okay, you want your shaft to be strong enough, okay, to withstand, to carry all the forces that it needs to carry. Okay, it should be strong enough to carry all the forces that it should carry. So when you are designing on the basis of strength, that's what is in mind. I do not want my shaft to fracture because it doesn't have enough strength. Okay? The second basis that you can design shaft is the basis of rigidity and stiffness. That is a case where deflection is much more important to you than strength. Okay, we will still consider deflection with our strength calculations. But if your matter is deflection, then you want your shaft to be very rigid. There's a design approach that is based on rigidity and stiffness. In this class, we don't have time to cover both. So we will spend time on designing shafts for strength is the core. Okay, all your shafts should be able to withstand all the forces that act on it and transmit the power it should transmit safely, without failure. Okay, so on the basis of strength, we itemize a few cases. We consider a few cases. Now, all of this, remember when we're talking about modeling, we talked about mathematical model, we talked about geometric model, we talked about physical models and all of those. And we said models are usually developed to represent a real life physical, object or occurrence or event. Now, in modeling, if you will consider all the factors in real life, your model will be very robust. It will actually represent the real life thing very well, but it will be difficult to manage, particularly in terms of computation. And so many assumptions are made. One of the things I give marks for in this class, and you will see, is assumptions. What are your assumptions? Because sometimes some things are not told you, you have to assume them. Is that okay? You have to assume them. All right, so the first consideration or the first case of designing shafts on the basis of strength is the case where we say the shaft is supported to twisting moment or torque only, no bending moment. Is that okay? What that means is we are saying that all the elements that you have put on this shaft and the shaft itself, they have negligible weights, and there is no external force that is acting on the shaft to cause it to bend. The only available force here is twisting moment or torque, the one that is causing the shaft to rotate. So a case where we reduce the case of a transmission to the only forces available are the torque, the turning, the force that is causing the shaft to turn. No weights, no bending moments, no axial loads. Then it's a very simplified case and an easy case to go about. Shaft subjected to twisting moments or torque only. Okay? We'll do detailed calculations when we as we go on. Then you have shafts that are subjected to bending moments only. So, in fact, we should have actually called them axles. Because if a shaft does not have torque, it means it's not turning. Are you following me? And we said that any member that is not rotating is an axle. When it's rotating, is a shaft. So when we have a case where you have a member that is not rotating, it has not been subjected to turning moments, twisting moments, or torque. Only bending moments are acting on it. Then that's a case of shafts that are subjected to bending moments only. There are formulas that simplify the scenario. Okay? Then we have a more realistic scenario where the shaft is subjected to both twisting and bending moments, both torque and weight loads. Is that okay? So this is more real. That your gears, your shaft itself has a weight that is pulling it down. All right. When you now add the rotating members on your shaft, the pulleys, the gears, all of that, they also have their own weights. Okay. So we now look at the scenario where we have combined twisting and combined bending moments. So you will see that the complexity of your equations will keep this, it gets more and more and more. Then we will now look at shafts that are subjected to axial loads in addition to combined torsional and combined bending moments. Okay, so in addition to the shaft rotating and to the fact that it has weights on it that provide bending moments, we also now consider a case where there are also axial loads. If your shafts are your gears are helical gears, then there will be axial loads. So how do we design such shafts to withstand all these three loads that are acting? Okay, now options or cases A, B, C, and D are built on the assumption that these loads, either the twisting moment or torque, or the bending moment, or the axial loads, the assumption is that all of them are constant over time, right? So if we say, oh, this thing is transmitting a torque of something Newton meter, is going to be constant. constant. So throughout the operation of that shaft, that torque will remain 400 and maybe 400 Newton meter. It will remain that. It's not going to change. That assumption is under A, B, C, and D. But in real life, no force is constant. Okay? So we now consider the fact that there is a shaft that is subjected to fluctuating loads in all these instances. Twisting moment alone, fluctuating loads. Bending moment alone, but that bending moment is fluctuating. Combined of this is fluctuating. Okay? Fluctuating loads, which represent much more what happens in real life. And like I said, as you move down, the complexity in calculation increases. And that's why in this course, we do not expect you to remember equations. We do not expect you to find the equation and apply it. Okay? Even the various parameters in the equations are sometimes even difficult to figure out. Where will I get it? Some of them you will do several calculations to find them before you come back to your main equation and plug them in. Okay? So these are the various cases we will consider when we start looking at that. Now, let's define a few things. We are going to be talking about maximum permissible working stresses for transmission shafts. Okay, we'll talk about all of these. Talk about maximum permissible shear stress. Okay, because these are the parameters that we require in our calculation. Okay, so what do we mean by the maximum permissible? Underline that word permissible. Okay, when you draw your what's that? There's one graph that you people usually draw with material science, BAM's graph. Stress strain curve. When you chart your stress strain curve, you can tell when a material is going outside its elastic limit. You can tell at what point the material starts exhibiting plasticity, all right, where a little force is causing a deformation that is not commensurate to that force, and the deformation does not return, right? That's when we get to the plastic return. And then you get to a point where fracture occurs, and you talk about your maximum yield. You talk about your yield stress, and then you talk about your maximum, what do you call it now? Maximum tensile stress. That's the point at which fracture occurs. Okay? But we are defining a maximum permissible. Okay? So there are standards, there are bodies that maintain these standards. They say, yes, we know that for this shaft, the maximum tensile strength or stress is this. That means that when you supply this stress to this material, it will fail. It will take it beyond the elastic limit to bring in the plastic limit, it will cause it to fracture, right? But based on where you want to use this shaft, this is the maximum permissible stress that we are saying. So you must not allow your shaft to have a stress that is beyond this. Okay? So according to the American Society of Mechanical Engineers Code for Designing Transmission Shafts, this is the standard. The maximum permissible working stresses in tension or compression. So if it's acting to cause your shaft member to be in tension, so imagine a shaft and you hold both ends and you are pulling them apart, that's in tension. Or compression, where you have compressive forces, instead of pulling them apart, you are pushing them together. The maximum permissible working, as this shaft is working, the stresses that are permitted may be taken as either 112 megapascals for shafts that do not have allowance for keyways. So you are coupling that shaft to its gears in a different way, not using keys. Because what keys do is keys chop out a portion of your shaft. And once you do that, you weaken the shaft. You weaken the shaft. So the maximum allowable permissible or the maximum permissible working stress in tension or compression, and these are normal stresses, not shear stress. We'll come to talk about shear stress later, is 112 megapascal. So if your problem does not state it, this is what you will take for a shaft that has no keyway. And this is when you don't have access to the material properties of that shaft. Okay? When you don't have access to the material properties of the shaft. Or if your shaft is going to have allowance for keyways, then your stresses are not allowed to go beyond 84 megapascals. So you see that it is lower. That tells you that your introduction of a keyway will reduce the strength property of your shaft. Okay? So when you have shafts that have their defined physical specifications already, then the permissible tensile stress that is shown as sigma tau or sigma sub t, as I've seen there, it may be taken as 60% of the elastic limit in tension. 60%, that means that, so I expect that you know what the elastic limit is. For this material, if we apply stresses to it, the stress that will cause it to leave the elastic region and enter the plastic region, that's the elastic limit, right? The elastic limit in tension, if we hold both ends of the shaft and we are pulling it apart, the amount of force per unit area that will cause our material to leave the elastic region and become plastic in nature. That means that it will not return to its original shape. Okay, whatever that stress is, we will take 60% of it. So we're not even allowed, we don't want to go anywhere near it. The permissible tensile stress in your shaft should be 60% of the elastic limit in tension. Okay, but it must not also be more. So we will check these two. We will find the elastic limit in tension. We'll take 60% of it. Then we'll find the ultimate tensile strength. This one, that's the stress that causes it to fracture. That's what is called the ultimate tensile strength. If you hold it and you are drawing it apart, the stress at which fracture occurs is your ultimate tensile strength for that material. Okay, so we take 36% of the ultimate tensile stress, and we also take 60% of the elastic limit in tension. We compare. Whichever one is lesser, that lesser value becomes the maximum permissible working stress. That's the working stress that you are permitted to develop, that is permitted to develop in your shaft as it is working. Do you understand? So the first condition is either 112 megapascals. If you don't have access to these properties, you don't know what the ultimate tensile strength is, you don't know what the elastic limit in tension is, then when you are given a shaft, just assume 112 megapascals if that shaft is not going to have keyways. But if it will have keyways, then it's 84 megapascals. But if you have the material properties, the physical specifications are there, you know the ultimate tensile stress, you know the elastic limit in tension, we will take 60%, 0.6 off the elastic limit in tension, right? And then we also take 36%, 0.36 times the value of the ultimate tensile stress. And then we compare whichever of these is less. But if we don't have access to the ultimate tensile strength, we just use the elastic limit in tension. If we know that one, 60% of it. If we don't have the elastic limit in tension and we're given the ultimate tensile strength, then we use 36% of it. Okay? That's one way. Now we're still defining more. For shear stresses are different from normal stresses. For shear stresses usually come with torsional loads, right? The maximum permissible shear stress, remember we said maximum permissible working, these are normal stresses. The maximum permissible shear is either 56 megapascals for shafts that do not have allowance of keyways, or 42 megapascals for shafts that have keyways that have been cut into them. But if you have the material properties, the physical properties, then we are considering either 30% of the elastic limit in tension or 18% of the ultimate tensile strength. Now, notice that these values, the elastic limit in tension, they are normal stresses. That's why we're not taking 60. We are saying 30% of the elastic limit in tension will be your maximum permissible shear stress. And 18% of the ultimate tensile strength will give you the maximum permissible shear. We'll check both of these and decide which is less. Now, over time, even when we have that, we introduce a factor of safety to reduce the value further down, to assure that no matter if somebody goes and is crazy and they adds more weight to this thing, it will still not fail, because we have said, we have calculated and we have designed it with a maximum permissible, which is way lesser than the actual shear stresses or normal stresses that will cause it to fail. Is that clear? Is that clear? Give me feedback.
Yes, sir.
All right. I will stop there. When we come next week, we will start with the how to identify forces and loads and draw your free body diagrams. I will take only one question if there is. Only one question if there is, and then I will have to go now. So if you have a question, just unmute yourself and speak, or drop it in the chat if you have a question. If we don't, then I move. All right. I will send to you these slides, right? I will also send to you the textbooks I use. I use Shigley, Machine Design by Shigley. It's a very standard book, and it's so the equations, when we come to the equations we use here, we will use the equations coming from Kurmi, those Indian guys, right? Because they are less complex at this level. Okay. If we use Shigley is a lot more robust. Okay. If I'm doing a design for real life, I will rather use Shigley. You can still use this, it's still okay. Okay, but if you want more accuracy, Shigley for me. But for the purpose of this class, most of our calculations will follow the format that the Indian guys use, because they also have a more they broke it down in simpler bits for people who are just being introduced to design the start. So when we come next time, we'll go into them. I will send you both materials, okay? Both, just the chapters on shafts in both textbooks, and then my slides as well, so that those of you who want to read ahead of the class, you can read. Those who want to do whatever you want to do, you can do. Okay, it looks like there was no question, and that helps me. Thank you very much. We will see next week. I don't know if by next week we've secured a class, then I may start coming back into school. If not, then we will keep doing it. Also, by next week, I will send you links where you can go back and watch these videos, okay, from my YouTube channel. Is that okay?
Yes, sir.
Great. So we will end the class there. Just a quick announcement. Tomorrow we are going to have a college prayer and fasting. The whole college, staff and students, we want to gather to pray and fast. I want to encourage you guys to please be in attendance. 1 p.m. tomorrow at the new auditorium. Please, as many of you as can come. In fact, invite everybody. We want to pray and ask God to stay the hand of death in the college. The frequency has become too much. So please, this is to invite you all and invite other. It's for engineering. Everybody, all the other departments in engineering are invited. Okay. Thank you, guys, and see you next.